So this kind of goes with a lot of, I mean, there's even more distributions that we haven't discussed. But there's very similar threads with how to interpret them. They have different charts and different numbers that mean different things, but they can be used in very similar ways. So we have this entirely new chart, chi-square, but it feels very similar to how we use the z-scores and t-scores to see if there's evidence or not, that kind of thing, right? So last time, what do you want from me? Okay, all right, just want me to push your button again, sure. We did this together. This is kind of related in a way to the z-star formula. So this is like our observations and what we expect. Sort of like, what is the z-score formula? It's x bar, which is our sample information. That's what we observed, minus the mu, which is what we would expect. Observed minus expected. So there is a direct connection between those two things, mathematically. That's behind the scenes. But this chi-square distribution, I tried to do something new. I try to get you to understand it exists by itself, just like a standard normal just exists. I can then turn raw data, I can turn sample data into z-scores, so I can compare them to other things on the z-score distribution, right? You guys with me so far with what I'm saying? So we convert sample data into z-scores, so then we can see how far away from the center it is and so forth. We can do the same thing with the chi-square. We can convert observations to chi-square numbers and see where they fall on the distribution. So that's what we did here. This was the example that I had already worked out. Distribution of M&Ms. And this was how far away it had to be to show evidence that it wasn't the same as this. So we have what we see. We have the claim, which is that it's uniform, which means they should all have the same number. Each color should have the same number if it's uniformly distributed. Right? So that's what I see. That's what I should have seen if the claim was right. And then I see how far away are all those observations from what they should have been. And altogether they came out to this. That's like Z star. From the chart, for degrees of freedom of 5, because there were 6 categories, and this level of significance, we found the rejection region had to be more than this. So that wasn't far enough away. So that's not far enough away from this to say that the population of M&Ms is not uniformly distributed. That one sample was a little off, but it's not by itself, it's not enough evidence to say the whole population is off.
So is it always reject the claim? When would you say support?
So on this kind of goodness of fit test, your null is always that. So here where am I at? Here, I got to get more than this to say that they're different, right? So the null is always that they're the same, and you're trying to show evidence that they're different. So goodness of fit are always like that. We're about to do today real hypothesis tests. So this one, I wouldn't even call this I'm not going to make you do all the steps for this. I'm going to make you do this, look this number up, and compare it to your number. That's the heart of the test. So it's more to the point. It's always the same. You don't even have to set your hypotheses up because they're always the same. The null is it is the same, and the alternate is no, they ain't the same. And we didn't get far enough away to reject that they're the same. So that's what this says. We have not found evidence to reject the claim that they are uniformly distributed. Okay, maybe. And then we did another example that was a little different, just to show you how it could be much more specific. This is the way that blood cholesterol levels are regularly distributed. And then I wanted to compare it to some little secluded area where they eat a certain type of diet, and we found out they were not doing very well health-wise. So we want to know what kind of diet to stay away from, maybe, right? So that's what we did the other day. Okay, cool. Let's do some real quick, I don't think I did this last time, some little quick fire finding chi-square scores. So let's do this. So everybody's got a chi-square chart now, right?
Yeah.
That would help. Oh, where did I put that piece of paper? Leave that for later. There it is. Okay, I'll use here. So let's find a chi-square where n is. Don't worry. Wow, okay, I'm trying to wait. Let's say n is, what you got, Jeff? 25. Alpha is 0.025. Let's try to find that score. So you have your chi-square chart. If you weren't here the other day, maybe just sit there for a minute. See if you can figure it out. Take a look at the chart, see if you can figure it out. So let me say this will be for like a goodness of fit, a GOF, goodness of fit test. Say again? You're looking it up.
Right.
All right. So I think everybody's had a chance. What do you guys get?
39.364.
39.364. All right, let me see if I agree with you. So we got alpha's 0.025. Degrees of freedom, 24. I like it. 0.025, 39.364. I love it. Kicks ass. So real quick, just to kind of, let me show you something, because we're about to transition into, so a goodness of fit test is always a how many tail test? One tail, because what I'm fighting against is that it's 0. So I'm trying to show that it's not 0. I'm trying to find evidence that the difference between what I see and what was predicted to be seen is not 0. So it's going to be up here, greater than 0. So goodness of fit test is always a one-tail test up there. Today we're about to transition into, well, what's it going to look like if it's what kind of things will be a two-tail test with chi-square. And this will be a test for standard deviations. Say I think the standard deviation is not equal to 5. How many tail tests should that be? If I think the standard deviation is not equal to 5. Two-tail test. I like it. So let's say I have a claim where the standard deviation is not 5. So it should be a two-tail test. Let's say that n is 17. It's known to be normal. Let me put that in the background here. Both of these, everything. N is 17. And let's say that alpha is, what, Jeff? I don't know, man. What are you always asking me these things? 0.01. Sure. I like it. So let's step through this together, because we haven't done this yet. So if alpha is 0.01, what area is in this tail? 0.005. I like it. What area is in that tail? I like it. And it's kind of silly because this chart always wants the area that's to the right of the critical value, right? I really want everything here to make some sense. So it's kind of nice the way this works. So to the right of this is 0.005. So we can find that critical score right now. So let's find that first, and then we'll worry about the lower one. So I call this one chi-square big, because it's the bigger one. So let's find chi-square big. What's my degrees of freedom? 16. 0.005, right? It's a two-tailed test, so you got to chop it in half yourself. Oh, too bad. Yeah, 0.005, 34.267. I like it. Let me stop there for a second. So 0.005, because I had to split the alpha into two tails. Is that cool so far? So the chi-square is not as nice as the t-score. It doesn't show 1 and 2 tail. Aww. So we have to know if it's a two-tail test, we've got to cut that bad boy in half. So I'm talking about 0.005. So that's the big one, 34.267. That's going to be here. How do I find this dude then? You said there was 0.005 in there, so what's to the right of it? 1 minus 0.005, which is 0.995. Notice something. What is that plus that? 1, of course it is. Did we just do 1 minus that to get that? Do you see what I'm trying to say here? Again, we're just getting into this. So if you looked up 0.005, why did we do that? Two-tailed test, I had to cut alpha in half. If you look up 0.005 to find the big dude, you got to look up 0.995 to find the small dude.
How do you know it's a two-tailed test? Are you going to tell you, or just because it's hard?
Because of this. We know that not equal to means, yeah, if I thought it was bigger than, that would have been a one-tailed test. Let me stop there for a second. I really want to, so part of what I'm talking about sounds old, but we're using this weird different chart that has no negatives. That's why some of this is a little weird. It's not going to be symmetric because it's skewed. It's not as nice as Z-scores. You can't just look up 1 and put negative on it. No, you can't do that. Yes?
What do you do with the 0.01 for the other one?
No. There is no 0.01. What's the very first thing I did to this poor guy, because there's 2 tails, I cut him in half. So he's there and there. Alpha is the total area in the tails, or the tail if there's only 1. So it's 0.01. So where is he? He's there and there.
What's up with everything at the top? I'm just trying to confuse how you're going back and forth.
Here's one example. Here's a second example.
All right, thank you.
Cool. So that's a goodness of fit test. That one's done. We're done with that one. Here's the second one. I like it. Yes?
Where'd you get the 0.995?
So are you cool with 0.01? So 0.05 there, 0.005 there?
Yeah.
This crazy ass chart wants areas that are where? To the right. Is that to the right? No, shit. So to the right is 0.995. If that's 0.05, what's to the right of it? Everything else. 0.995. How we doing? Ooh, you guys love it. You're like, come on, Jeff, it's the end, man. Make it easy. I can't. Well, this is it. This is what we got to talk about. It's too bad. Again, how many examples have we done so far? Not many. All right, so we're going to do some more. I'm not sure exactly where I'm losing you guys here. It's a two-tailed test, so I got to cut this guy in half. Everybody must be okay with that. Okay. So there it is. Cut it in half. Cool. Two-tailed test because it's not equal to. We know that. That's a two-tailed test. This crazy-ass chart wants areas, only understands areas to the right of it. Oh, shit. Okay, so I can't use that for the lower one. I've got to use 0.995. So what's that mean in here now? The big one we already did. It was 0.005. And the degrees of freedom was 16. So we got 34.267. Now watch. Watch the beauty of the symmetry here. If I look here to get the big one, I look here to get the small one. If I looked here to the big one, I would look here for the small one. Because what's 0.99 plus 0.01? 1. That's why they set this chart up that way. So this looks like one tail, the other tail. And as I move in, my alpha's getting bigger as I move in. All right, so we'll do a couple more, but some of you guys kind of see what I'm saying. So for the big ones up there, it's going to be equidistant on the other side, 5.697.
No.
Oh, did it go up? Oh, 5.142. Thank you. There you go. I like that. That's even. I wish I could say I did it on purpose, but no. This guy screwed it down. So degrees of freedom 16, 0.995 to the right gives me 5.142. So just to kind of close the loop here, this is my rejection region I just drew. So if chi-square would be less than 5.142 or greater than 34.267, we would reject the null, support the high. I like that face you made. That's awesome. All right, let's do another one. I can do that. I need more paper. Let's see. More paper. There we go. Okay. Yeah. All right, here we go. You ready? Let's do another one. What if I had a claim Let's do another two-tail just to make sure. What my claim was sigma does not equal to 1.3. Let's say that n is 51. Let's say alpha is, what you got, Jeff? I don't know, man. Keep bugging me. 0.10. Find your rejection region. The main difference is my rejection region can't include negative values. Of course it can't. Chi-square is always positive. It folds the negative side on top. So it's not symmetric. It's skewed, plus it can't be negative. But the underlying idea that gets me to these numbers is the same. It's just that the numbers are going to be not what I'm used to at all. So there's my rejection region there, right? The regions. How much is in each?
0.05.
0.05. I like it. So how much is above this? 0.95. What's my degrees of freedom? 50. All right, let me just give a second. Just make sure everybody got those right. So now looking at the chart, degrees of freedom, does it go up to 50? Thank God. Okay, good job. See if I can keep this on the heel. 0.05. Look how nice it is. The chi-score that goes here is on this side of the chart. Holy shit, that's nice. Right? Alright, so chi-score big, this one. I want to look at 0.05 and then go down until I hit 50 and I get 67.505. Cool. Now what about chi-score small? Cool, I like it. So you look up, so again, I want to really hammer this home. I looked, oh shoot, I lost my degrees for, I looked at 0.05 to find that, so I'm going to look there. So I'm going to look there, and I'm going to go down to 50, 34.764. So that's my full rejection region. How would I say that in words?
Chi-square is less than 34.
Reject the null, support the high, blah, 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 blah. So this is step 3 in the huge hypothesis test step scheme. Okay, maybe. What was I going to say? Oh yeah. So here, instead of putting like a star on that and making it like chi-square star, I just call this chi-square big and chi-square small to differentiate it from the chi-square I calculate. So I just call the chi-square I calculate, I just call it chi-square. Okay. Maybe, yes. Oh, I'm sorry. You guys in the back are like, can you share that with us? I guess so. Alright, so let's try an actual problem. Now obviously, let's do one more of these. If it was a one-tailed test, let's see, make sure everybody's with it. Let's say sigma is less than 59.2. What's the only thing that currently tells me for what we're doing right now? How many tail and where that tail is. It's less than, so I know the tail's going to be on the chi-square small side, right? So let's say that n is 11. Let's say that alpha is 0.10. I like it. So you're going to cut that off in half? Of course not. You only got one tail. Yes, sir.
The tail would be on the lower end.
I like it because you're saying less than. So it's going to be down here. Kind of like the opposite of the goodness of fit test. And why does it make sense? Can a standard deviation be negative? No. So it's kind of like 59.2 would be in here. This is where somebody thinks it is, and I want to show that it's so much less than that, but I can't go negative. So that's why the picture has to represent these values that can't go negative. It exists all on one side, so the numbers look different than we're used to, right? All right, so how much is in this tail? And what's the actual number I want to look up?
0.90.
0.9!
10.
No! Okay, that was remarkably interesting. Degrees of freedom is 10. I like it. So I go to 0.90. Stop at 10. 4.865. So my chi-square, if chi-square is less than 4.865, reject the support the blah, blah, blah. Alright, so now let's do an actual problem together, and then of course you know me, I've got a handout where you guys get to do one on your own.
Thank you.
You're welcome. Let's take one right out of the book here. Let's see what they got for us here. Okay, let's do this one here. All right. It's on page 614. Well, at least in my book. I don't know. Your books might be a different page. This is in the chapter 11 homework number 65 through 68. Don't worry about p-values for these. That requires technology, which your old-fashioned teacher, just doesn't want technology. Sorry. It's awesome, but it doesn't help when you're learning. So here, I zoomed in way too much. No, you froze it, Jeff. There, see, that's a good example of Jeff and technology. Okay. So the average waiting time varies. The standard deviation is 3.4. A random sampling has a standard deviation. One doctor believes the variance of waiting times is greater than originally thought. Okay, cool. Doesn't that sound like normal hypothesis test? It's just that the difference is this is dealing with standard deviations. And a real quick word on this. With normal hypothesis tests, I make a claim about a mean, right? And how are means distributed? What is it that tells me how far apart on average the means are? Standard deviation, beautiful. So the standard deviation is what actually makes this picture work. So if I want to test this, I can't use this picture. Does that make sense? That's why we have a whole different distribution. We have this chi-square distribution that exists on its own that I can then use to test standard deviations out with. I like it. Maybe. Okay. The one thing I'm missing to do this problem is I don't have like the M&M problem. It's not the same. It's not a goodness of fit. And very much like we have this z-score formula, but we also have this z-score formula. And for that matter, we also have this z-score formula. P bar, Q bar, blah, blah. I mean, but they all become Z's in the end. So we have multiple ways of calculating Z-scores based on the situation I'm in. So we have this chi-square formula we used the other day. Become a 2. Get out of here. But that's not the situation I'm in, is it? No, it ain't, Jeff. So we're not going to use that one today. We're going to use this one. So what's a Z-score normally do? It takes a raw score, my sample, and makes it into a Z. So what's a chi-square supposed to do? Take what I see and turn it into a chi-square. So when I take a sample, what am I going to see? S. Or S squared, right, for my variance. So if I plug it in here, I'm going to convert that into a chi-square, and then I can compare it to my critical region, my rejection region, see if it goes far enough away or not. Let me stop here for a second. You guys are like, you can just stop, Jeff. No. All right, so this is exactly like the like the next Z-score formula we learned. Now we got that chi-square for goodness of fit. That's the one I want to use for testing standard deviations. I probably need a formula that's got a place for standard deviations to go. Okay, all right, maybe. Okay, so here we go. Has everybody got what you need from this written down somewhere? So what's S? What's S? 4.1, good. What's sigma? 3.4, kick ass. And 30 is? N. Beautiful. And what's my claim? Or what's somebody's claim? Yeah, sorry. Holy crap, did I just throw it in? Okay. Where'd it go? There it is. So real quick, we got S is 4.1, sigma is 3.4, N is 30. My claim, sorry?
It's greater than
Who to what's greater than who? Sorry?
Waiting time is greater than 3.4.
No.
Sigma.
The variance of waiting times is greater.
So sigma squared.
Sigma squared is bigger than.
3.
Now here's where it's a little mean. Let me. So I know the claim is about the variance, but I've got sigma here, right? So normally we convert this claim to be about standard deviation. So if you put sigma squared, why could you not put 3.4? Because that's sigma, it's not sigma squared. This problem's a little evil, but that's all right. So the claim is really, if the standard deviation is bigger, if the variance is bigger, then the standard deviation is bigger. It's the same thing. I just said the same thing twice. Do you guys understand what I'm saying? Those numbers they gave me, the 3.4 and the 4.1, are they variances? Are they variances? No, they're standard deviations. It says right there, it's a standard deviation. What's the difference? Well, one is sigma and the other one's sigma squared. Oh shit. So I know that they said one doctor believes the variance is greater, but I'm going to write that as sigma greater than the number they gave me. If the variance is bigger, then so is the standard deviation, right? You guys still don't like that. How it says, if x squared is bigger than I thought it was going to be, that means x is bigger than I thought it was going to be. That's all. So instead of writing sigma squared, my claim is sigma greater than 3.4. Why does what I found so far look good? Bless you. What did we find from our sample? No, we found that S is 4.1. So thank God that at least seems to be in the right direction. If you got S to be 2.7, then screw it. I'm not going to do the test. I am obviously wrong. Or at least that sample doesn't show evidence for what I believe is true. Maybe. Okay. So that is at least in the right direction for this claim. So that's the claim. So which one is that?
High.
The high? I like it because it does not have a equal sign. I like it. Some of you guys are like, no, dot H, no. All right. So sigma. So the ho is going to be less than or equal to. I like it. So we're going to truncate this a bit. We're just going to get to the point here. no matter what the hell the book says, because the book forgets sometimes, it's got to come from a normal distribution. And we have one option, chi-square. So there's no points z or t. That's out of the question. It's just chi-square or nothing. So screw step B. All I'm going to worry about is set up the rejection region, calculate your chi-square, and then just tell me what you found. So what do I mean by that? What do they tell me? Do they tell me? Let's make up some shit. Let's say that. Oh, here it is. 5%. Sorry, it's in one of the questions. So alpha is 0.05. Let's set up the rejection region. Alpha is 0.05. What's my degrees of freedom? 29. I like it. How many tail tests? One tail. And where's it going to be? It's going to be up here. I like it. Cool. Pretend like that doesn't cross. So take a minute and see if you can find that critical chi-square score. Oh shit. You probably want to look that way. One tail, so you don't have to split that alpha up, right? It all goes into that one tail. So has anybody found that yet?